Good afternoon, and welcome to today's webinar, The Future of Mobility and Shifting Manufacturing Requirements. My name is Maria Ma, the Marketing Campaign Coordinator here at engineering.com, and I'll be your moderator today. Before we get started, I have a few housekeeping items to cover. Today's webinar will be recorded, then available for on-demand replay on engineering.com. Your PDH certificate will be emailed to you 24 hours after this webinar. If you have any questions, you may submit directly in this webinar interface, and we'll try to address all questions during Q&A. If we run out of time, we'll be sure to follow up through email. Now, without further ado, I'll pass it over to our presenter, Marketing and Alliances Director for ESI, Eric Kam. Over to you, Eric.
Thank you very much for that kind introduction, Maria. And today's topic, as you mentioned, is the future of mobility and how a lot of the goals and ambitions of the future of the mobility market are really shifting how we are requiring the manufacturing design to be made for these modern vehicles. So when it comes to when we picture the future of mobility, there's a lot of different things we could talk about: e-mobility, autonomy, there's even some people talking about individual personalized flight as being part of the equation for future mobility. And in that regard, that certainly creates a lot of pressure to engineer and develop the use of the lightest body material in order to address the range anxiety that would be brought upon by most vehicle electrification issues. And what we're seeing is that certainly back in, before electrification was the topic of the day, it was always advantageous to try to find a way to make the vehicles a little bit lighter. And we talked about fuel economy before and how making cars out of lighter, stronger materials was very important for making the most out of our gas mileage. But now with vehicle electrification, there's even a greater emphasis on taking the kilograms of the body and transferring those into things that add more value to an electrified or autonomous vehicle. And it turns out that with this shift from petroleum-based internal combustion cars towards battery electrification or maybe even fuel cell electrification, is that the cost per kilogram or the benefit per kilogram shaved off of an auto body even becomes much higher than what it was traditionally for an internal combustion traditional bodied car. So we're seeing a great deal of pressure on the automakers, on the industry, to try to find a way to develop lighter and stronger body structures, because every kilogram that I can take from the vehicle body and shift towards the battery and the drivetrain, which turns out to also augment the stiffness and the strength of the overall vehicle, we're seeing a lot more value if we can shift that. And that's changing a lot of the way that people are envisioning the cars of the future being manufactured. And what I'd like to talk about today throughout this webinar are some of the challenges that we're going to be facing as we shift the auto body manufacturing from where it's been for the last 100+ years since the advent of the automobile globally as a industrial good. And we're seeing that there's going to be a lot of shifts from the way we're used to making things to how we possibly want to make them in the future. And that's really the crux of today's presentation. And I hope that it will be enlightening and informative for all of you. So I'm going to start off with this relatively famous quote that is allegedly attributed to Henry Ford. And back in the day, people said Henry Ford was quoted as saying, "Any customer can have the car painted any color that he wants as long as it is black," right? And that's the quote that I often read online attributed to Henry Ford, right? But the question is, why? Why was it important to restrict the choice of color to black? And it turned out that one of the reasons why all of those Model Ts were painted the same colors that allowed them to optimize the production. By picking a paint color and paint formulation that optimized the fastest amount of drying time on that assembly line, they were able to standardize the assembly line speed and rate of production. Now imagine if we tried to put the kind of flexibility that we offer today in different paint colors, but that also meant different paint drying times or curing times back in Henry Ford's day. That meant that that conveyor line that was moving the cars through the assembly line would not necessarily travel at the same speed on the days they're producing black cars versus white cars, green, silver, or red. And that would not have allowed them to optimize what we think of today as mass-produced auto manufacturing environment. So I want to take a small parallel to that when I consider what that means in today's auto industry, right? And here's a quote that you could attribute to just about anybody who worked in the auto industry for the past 100 years. That quote would have been, you can have a car of any material you want as long as the bodies are stamped sheet metal panels welded together for subassemblies and then assembled as on body, body on frame, or unibody, right? Because that's the conventional way cars have been built for the past century. That every time you talk to people about automotive body, the phrase body in white, then immediately they'll think sheet metal, if not sheet steel only, they'll say sheet metal, and that those are all stamped sheet metal parts that are being welded together to create our auto body. Right? And again, the reason why is that the product performance and the production capabilities have been well balanced for the past century. That making a automotive body as a assemblage of, in many cases, several hundred individual sheet metal stamped panels that you weld together, that's been outperforming most other proposed technologies for the past century. Now, I know before I get too far, people could probably object right now and they could raise their hand with a question saying, well, weren't there examples of people doing things that were not stamped sheet metal bodies throughout the history? And of course, we could probably each raise our hand and think of a handful of them. But the reason why we can do that is because it was exceptional. It is not the rule that we're using sheet mold compound for the external body panels, unless you're remembering Saturn from back in the 1990s, right? People are not using a high degree of composites in mass-produced vehicles because we could name a few examples, a few exceptions, but those would be exceptions to the rule. And that's because for the past century, sheet metal stamping and welding these bodies together in a semi-automated or fully automated assembly plant is the best way for us to get that balance between the performance of the safety and the strength and the structural integrity of a vehicle that we wanted with the right mass of the vehicle that we wanted and the right cost performance for that. But now when we think about our goals for trying to make vehicles even lighter, even stronger, and not sacrificing the strength in order to make those cars lighter or to pack a few more kilowatt hours of battery into a vehicle, we really need to find more aggressive ways to wring out a few more kilograms out of each auto body. Right? Because the things that we're thinking about in the future, right, are really new ways of looking at vehicles and addressing things that we hadn't done in the past. So I'm going to start with a couple examples. This is just gleaned from me going through and looking up the latest automotive news or Ward's Auto World and some of the news that they've had about the changes in the production materials for lightweight bodies. So you can see in the top image, we have a couple areas that I circled in purple, and those are areas where we're seeing use of die casting as a manufacturing technique to replace some of those complex subassemblies that made up the automotive body. We can see that there is use of die-cast aluminum showing up in a variety of materials or even die-cast magnesium alloys. I've been seeing mention of die-cast aluminum being used for the shock towers and the shock strut reinforcement areas of the vehicles, as well as the what we might have thought of as the engine cradle and those chassis components. We're also seeing the introduction of potential composite materials. Lately, we see people talking about replacing the traditional multi-body stamped, then welded together, floor pan assemblies, seat pans, seat risers. Those things were normally made out of several sheet metal components that were stamped independently and welded together. And now I'm starting to hear people say, well, why don't we just make that as like a monocoque out of aluminum, or excuse me, a monocoque out of composite materials? And that way we could have a very, very light floor pan, a very, very light seat reinforcement or seat riser, without adding all of that additional weight that would come along with the traditional sheet metal version of those parts. On the right-hand side, you can see different people were proposing and actually bringing to production recently aluminum high-pressure die casting for things like lift gates in relatively mass-produced cars like a C-Class station wagon. We can see examples of shock towers, and this one I'm pointing out to a reference of the Audi A7 and Audi A6 using aluminum high-pressure die casting. But I've recently read a few articles about how Ford's been using that to address some of their mass savings, as well as a space-saving design for their Ford Explorer sport utility vehicle. We're seeing examples where entire truck bed boxes are being put together with a mixed material structure, where we're seeing a mix of glass fiber reinforced carbon fiber composite materials. We're seeing steel, aluminum mixed into what normally was an all-steel body structure inside of a vehicle like that GMC Sierra truck box. We're seeing vehicles such as the proposed Chevrolet Malibu and the Cadillac CT6, where they're looking at a mixture of steel, aluminum extrusions, die-cast aluminum, making up the bulk of these automotive bodies. And we're also seeing things like that passenger bus in the upper right-hand corner being made of large composite panels to replace what normally would have been an array of different sheet metal parts stamped and assembled to make up that vehicle body. So one of the things that we see in trying to address these goals of future mobility and what they're trying to do to reduce the mass of the traditional automotive or transportation body by embracing some of these novel manufacturing techniques like high pressure die casting of aluminum, the use of carbon fiber reinforced plastic, is to help drive down the mass going into the auto body so that they can put more mass into the battery, into the motors, into the passenger compartment itself, to put mass where the value added really is. But this brings a lot of challenges to us. One of the challenges facing the transportation industry as they address these shifting manufacturing requirements is that they have to be able to predict with confidence the individual part production and the feasibility of the parts and the piece part costs of those individual parts. And they have to do that very, very early. And they'll need to be able to anticipate potential production issues arising from the as-designed geometry versus the as-engineered manufacturing requirements. And they will need to address and mitigate challenges with joining these dissimilar materials with very different assembly, different materials to address these assembly distortion issues that could happen. And they need to do all of this early enough to make a difference. Now, one of the challenges that I didn't list in those bullets is that because we have over a century of experience manufacturing cars, where the assumption is the entire body structure is stamped and welded sheet metal, a lot of the infrastructure of our product manufacturing and our product design organizations is structured on that core assumption that even when you talk about manufacturing an automotive body, and we know that there are already mass-produced vehicles that are using castings in their mass-produced auto bodies, that when you mention that to the organizations that are charged with doing that, you will find that all of the casting expertise lives in a different organization far away from body. right? And when you talk to people about casting, and if I go to any automotive OEM and I say, I want to talk to you about your casting manufacturing challenges, they'll send me to the powertrain organization. They won't send you to the body manufacturing organization. When you talk to somebody about, you want to talk to them about plastics and composites, they don't send you to the body organization when you want to address their problems about composite manufacturing. They send you to the trim organization, and they don't look at those trades as being part of the core manufacturing skill set that makes up auto bodies. And that's one of the probably overarching challenges that we face today, is that the individual automotive OEMs and much of the supply chain are all serving the industry where the manufacturing method is what dictates where that product goes onto the new cars. And now that I'm mixing ideas like we're going to put casting materials in with the body, now we're mixing disciplines, right? Body used to just be a stamping world. And now body is a stamping, and casting and composites world is a very transformational thing that the industry will have to address. Now, this is not unprecedented, right? We're not talking about anything brand new. I did a little bit of research, and I found out several years ago that Magna, who is a major automotive tier 0.5 or tier 1 supplier to the industry, they had already proposed this idea of making a multi-material door many years ago at a lightweighting design conference, talking about lightweighting automobiles. And they had proposed making this mixed material ultralight door design where they would be able to design a door that was functionally the same performance and everything we expect for a door closure to do, but it was at a 40% reduction in mass. And they were doing this by mixing things like stamped sheet metal, high pressure die cast aluminum materials for this A-pillar reinforcement, introducing a mix of stampings with extrusions in with the normal conventional stamped sheet metal, as well as high strength materials such as warm formed aluminum for this door reinforcement beam, and maybe the use of some advanced high strength materials elsewhere in the panel. And that brings up a big challenge, as I mentioned, already for the manufacturing industry to address this closure panel, which is presumably on just about every other car that you and I touch every day. It's all stamped sheet metal with trim attached to it. And now to present this idea that an integral part of a vehicle, such as their closures, could in fact be made up of a series of materials. And for that Magna example was predominantly cast material, extrusion, and stamped sheet metal, because those are materials that Magna is most of the time involved with in the supply chain. Now, I've introduced on this slide a possibility of a similar door that we're using stamped sheet metal, high pressure die casting, and also composite materials as well to make up that door, right? Because maybe we could talk to other automotive suppliers, other members of the supply chain, who instead of just focused on sheet metal and metal fabrication, was instead working on that full range of materials. And that's what we would like to address today, is that if we are going to address this idea of multi-material manufacturing, what I'm proposing is that we do this in the context of what I'm going to call the ESI door. The ESI door is similar to that door that I showed from the Magna Group, is a door proposed to be manufactured out of a variety and range of material manufacturing domains. So we've introduced traditional sheet metal stamping. We can stamp the door inner and the door outer out of sheet metal, in this case, high strength steel and dent resistant steel. And that's very typical for a typical automotive body, conventional automotive body. We could introduce an advanced high strength steel striker reinforcement, but now we could mix it up a little bit by proposing a die cast aluminum pillar reinforcement similar to the one proposed for that Magna door, because maybe we can create an even lighter weight pillar reinforcement if we use die-cast aluminum to replace what in many cases is a mixture of many different stamped parts to create that reinforcement. And now we could have a single component taking the place of a more complex multi-body stamped and welded body. Similarly, in this case, we've proposed a cross member, but our high strength cross member maybe we'll propose making that out of a composite material. Now, each one of these materials, as we introduce them in the context of this door, if we just expanded this door analogy out to be the entire vehicle body, would raise a variety of manufacturability concerns. When it comes to sheet metal stamping, you'll always hear from people two primary concerns: formability. Can we make the product without it splitting or wrinkling due to the manufacturing process? And what's its spring back going to be like, right? Spring back is this idea that all stamped sheet metal has this tendency to spring back towards its original shape after deformation, right? So that's a common issue that people are used to addressing when they talk about manufacturing traditionally stamped body in white. But now when we introduce things like this, I don't know, this die-cast aluminum pillar reinforcement, it has many different challenges that come up as a result of its manufacturing process. Certainly, one of the biggest challenges that people have faced when they talk about manufacturing die-cast for body is they immediately start talking about cycle time. Most of these stamped panels are talking about cycle times where we're producing anywhere from 10 to 20 parts per minute. So every minute there are 10 door inners and 10 door outers being produced in a conventional stamping line. And then they immediately look at, well, die casting, we're not going to get that same kind of turnover. But what they forget sometimes when they talk about these production throughput rates, these individual part production rates, is that if we design correctly a die-cast structure that takes the place of many different stamped assemblies, then it's not necessary that we produce it at 10 or 20 parts per minute if it's taking the place of 10 or 20 different components that get welded together, because then its cycle time is also taking into consideration the time we would invest in packing those individual stampings up, shipping them off to a welding supply house, having the different welder take all of those different parts, piece them together, create all the welds, and generate the finished subassembly. Right? So one of the things that we have to address is this whole idea of these production rate challenges and how are we accounting for the cost of the different amount of overall operations that get invested to create a single component like that die-cast aluminum pillar reinforcement. There's also some challenges that we have with the metallurgical production to performance rate, that maybe certain alloys of aluminum are difficult to reach this high pressure die casting rate, and that perhaps there might be this mismatch that somebody might have assumed we were using a certain metallurgical mix of aluminum for its final part characteristics, but then maybe overlook that in order to manufacture that die cast part, we would try to choose a different formulation metallurgically to reach that goal. And there are a lot of unanswered questions when it comes to joining and assembling a die-cast component into a closure like this door, as opposed, as thinking about, well, how do we join it? Will it metallurgically bond well or weld well to the other panels? Let's also take a look at this idea of using a composite cross member. Composite cross members also have potential for raising many production rate issues that most of the time our near mass production of composites are still quite a bit of hand controlled, manually controlled processes trying to keep a track on how do we layer the composites together. And that many times people talk about production rates for composite parts not as not even in the same ballpark as the production rate that I was talking about for stamping of 10 parts per minute. But now people are talking about, in some cases, maybe it was 10 minutes per part. And how do we align these different manufacturing domains, these different manufacturing processes in order to combine into a single manufactured good. And all of these are challenges facing today's automakers as they address this idea of mixing materials. So first of all, I do want to mention that, in this case, let's talk about casting. People talk about casting and is it plausible and is it realistic that we can mass produce these mass reducing parts like a cast chassis or cast body structure in an automobile, right? And a lot of people have said it's just not reasonable that we could ever meet the production rates necessary to support these large automotive mass production schemes. And to challenge that, I'm going to quote one example in the slide presentation, and I'll mention another one, the Tesla Model S. The Tesla Model S has these two cast body structures. You can see them in the very top and the lower right-hand side of the slide. And those are aluminum die-cast chassis components, and they are certainly what we would consider a mass-produced vehicle. Now, the Tesla Model S is really allowing people to reduce the mass and increase the stiffness of this part of the body structure of the Tesla Model S. They've been able to get a lot of efficiency gains in recognizing that every time you cast this complex chassis component, that you are replacing a multitude of individual stampings, or in some case, maybe it might have been individual hydroformed rails or something making up a similar architecture body structure. If you were doing it that way, you would still have a much more complex manufacturing environment, because instead of being two large castings that made up that part of that body, it might be 20 or 30 individual stampings, countless number of spot or seam welds that would have to put that thing together. So we have to make sure that we account for, sure, this is a much more expensive individual component, but when you think about the number of components that it replaces, and then the number of manufacturing, sub-assembly operations, and final operations that it's combined into one manufacturing process, a lot of efficiency can be gathered that way. We also have to take a look at the mass savings that is possible from this material selection, because making this out of die-cast aluminum, they're certainly able to reduce the number of parts that they're ordering, but also the unnecessary overlap of material every time you try to join different parts together into a sub-assembly. So it's super efficient what they've done with the Tesla Model S. I've recently read a similar case where they did this for the Ford Explorer, which is a high volume vehicle and a vehicle that I suspect is going to exceed the volumes that we might be talking about with the Tesla Model S. In that case, they used high pressure die cast aluminum to replace the shock tower subassemblies that are in every single car. This allowed them to achieve two things. One, they were able to rearrange the construction of the engine compartment as well as the passenger compartment to allow for a more spacious passenger experience inside of the vehicle. But they're also able to take a shock tower, which is, conservatively speaking, probably about, per shock tower, at least 10 different stamped components that are stamped individually, then sub-assembled and spot welded and tack welded and seam welded together. And they were able to achieve a much more efficient use of material and space in that car. So now let's talk about the challenges in the casting industry. So if we want to think about how casting works, is that we have to balance the designed intent of the part as far as its part integrity with the mechanical properties of the alloy of material that we're talking about, its ability to be a well-defined, well-controllable process in the manufacturing environment, and to have a good tool life throughout the production of that vehicle. And also take into consideration that when we think about these body components, these are highly complex designs trying to fill the performance that was previously being achieved by a assemblage of multiple parts. Right? So we need to be able to predict in advance, is the manufactured shape even possible? If I take together all of the geometry that I need to have a performant part, a light enough, strong enough part, can I predict in advance that you can even get liquid metal to move in the way it needs to fully define that product shape? And can I do so in a productive and profitable way? Can I achieve that high enough throughput and efficient enough use of manufacturing resources that I can, in fact, produce the part as necessary to be productive and profitable? And make all these decisions fast enough and early enough that I know that I can go forward with this design or not. So some of these challenges in introducing die casting into the body is that these die castings are being designed to replace entire subassemblies and complex structures for cost savings, but that also increases the make or break pressure on the manufacturability confidence. Because if I'm talking about, that shock tower in the Ford Explorer, and if I was doing this in a conventional stamped and welded manufacturing, if that shock tower did in fact have a manufacturability issue in one area, sometimes I can still change an aspect of that stamping or that stamped assembly without severely impacting the cost of tooling, the cost of production, and even the entire product design itself along the way. But now if I introduce this complex die casting to replace all of those different stampings themselves and those different subassembly operations, if something is found very late in the game to make that die casting impossible, then I run a higher risk that I just end up with nothing manufacturable in that shock tower. Instead of asking for a small engineering change in a little bit of a reinforcement bracket or in one area of the stamping, I'm talking about major redesign of the product shape. And that could be very disruptive to our go-to-market confidence for these new vehicles. Another problem we have is, well, there's a lack of deep historical experience in addressing the manufacturing of castings as they contribute to a body in white. We don't have a lot of expertise, and many people inside of the auto industry who are very used to using castings right next to sheet metal stampings, right next to composites as making up this body in white. They're not used to that. And that's why we see all of our casting expertise is there in the powertrain department, there in the engineering department for the engine compartment, but not for the people who are worried about body. And that's just that's somewhat caused by this organizational inertia, that the body manufacturing organization is now just completely organized on this manufacturing process, that the body department is synonymous with the sheet metal stamping department at many OEMs and many suppliers. And that when you think about the foundry and the casting department, they would just say that that is synonymous with their powertrain organization. And that's something that can cause a lot of disruption in us trying to implement this technology. Also, this is very disruptive to the idea of how we normally treat our supply chain, that we normally know that far in advance, we're going to rely on a certain subset of the vehicle structure to be supplied by specific suppliers. And those suppliers are almost all organized by the way that they think about these different manufacturing processes. And of course, a lot of problem comes with this mismatch in alignment between piece part costs and production costs, because every time I take an individual stamping and I engineer that to take the place of welded together subassemblies in the body in white, Sometimes I don't think that we're properly accounting for piece cost when we recognize that by making this complex component replace an assembly process later on, are we really accounting for the savings that we're getting by eliminating all of those welding and subassembly operations at the assembly plant by buying a more complex stamping? A lot of times people would say that's too expensive. And the same thing goes for a lot of these cost benefit measurements that people make when they try to insert a die cast component into the body. So we introduced this idea that body manufacturing will need to, as early as possible, take into consideration the manufacturability of these body products, right? So they will have to very early be able to validate that the geometry of the part and the material properties of the part, as defined by its role in the performance, is a good fit for, can the tool actually be filled with the molten material at the right production weight? Will it cause or will it trigger the right behavior when it comes to the cast material solidifying? And will we have product performance issues and product shape fixation issues triggered by these challenges in turbulence and solidification behavior in our cast materials? Will we have the right microstructure once the material has fully cooled so that we have the right product performance without introducing any sort of distortion or residual stresses that could cause our completed product to have the wrong performance characteristics? So at this point, just want to introduce, I mean, this isn't a body component, but this is no more complex and no less complex than some of the body components that I suggested could be replaced with high pressure die casting in the future. And one of the things that helps introduce this idea of, can we have high pressure die casting do the right thing for the body manufacturing, is to see if we can increase the production rate. So here's an example how we were able to use predictive analytics to show that we could convert a previous single cavity die casting, which would have had a certain expectation for production rate and piece cost and investment for the supplier to supply it. And now we're able to validate in advance that they could effectively double their production throughput if in fact they moved from a single cavity casting to a double cavity casting. Similarly, I have examples from some of our other automotive customers where we've allowed them to go from a 4-cavity casting to as up high as an 8-cavity casting, right? And this is the kind of things that'll have to happen for these die cast components to be able to fill the gap of the production rate expectations that people have for these body components expected in body in white and casting. The other new material, or the other novel use of material that we introduced in the ESI door, is this idea of doing carbon fiber, right? Carbon fiber too is one of those things that people say, yeah, I'm sure it's good for aerospace and supercars and these specialty project cars, but it's not really something suitable for mass production. However, GM is reportedly considering using carbon fiber in the beds of all their pickup trucks. Or actually, this is relatively old picture, and this is already their current GMC Sierra pickup truck, right? So now when we think about composites and what challenges composites represent if we want to use them or integrate them into our vehicle bodies and our body structures, is how different composites engineering is from other ways of engineering vehicles. One of the things that I've learned in my recent education about composites is that this idea of product design and material selection, these things are totally inseparable from also considering the manufacturability of that component. That it is impossible to decouple this idea of just a net-shaped composite and assuming that it's crash-worthy without somebody having to be able to prove that that composite structure is even plausible, just from getting the alignment of the glass fibers to be correct and the type of resin and the behavior of the resin. So this idea of engineering individually, the product design, the material selection, and the manufacturing, you can't separate those when you think about composites. And that this iterative loop between product design, material, and manufacturing is always concurrently going on for all manufacturing. And that it's nearly impossible to assume that it's good without doing some amount of physical testing, and then again proving that the manufacturability of that part is also correct and achievable in the physical world. And this has been a challenge for many people in trying to figure out, how do we mass produce composite parts to satisfy the needs of the auto industry? So that means that in order to address this, we have to do our best to address those challenges in advance. And I apologize, that slide advanced on its own too fast. But one of the challenges in composite manufacturing is that, again, just like casting, if we are designing that composite body to replace a whole set of other individual stampings and subassemblies, that really drives up this pressure that every composite body component is really make or break. You really have to know that that individual part is feasible far enough in advance for you to know whether or not you're replacing those other components out of sheet metal. We do still have this lack of historical experience of people in the auto industry who've been working with different resin formulations, different fiber types, different manufacturing modes for these composite carbon fiber reinforced plastics materials. We do still see that this idea of having a body organization look at more than just sheet metal stamping is going to be a challenge for many organizations. And we see that this idea of suppliers of body components is really just kind of focused, hyper-focused on, oh, they work in sheet metal and automotive, then they can do body. But as soon as you introduce the fact that there might be composites in that body, then the sphere of people who already have experience in that in industrial scale shrinks. And finally, one of these big challenges is that, this mismatch between the expectations for individual piece part production rates and piece part costs when you think of these composite materials and composite bodies might be replacing large subassemblies and multiple stampings and multiple assembly operations. And are we accounting for that properly when we suggest what is the right piece part cost for a composite product? So early enough in the manufacturing scheme, we do have to make sure that we are in fact predicting that these composite materials are manufacturable in of themselves, right? Are we getting the right production rate out of these materials? And will these materials behave properly when we take the individual fibers into sheets of fibers and preform them into their shape? And one of the things that, one of the reasons why we say there has to be such a tight alignment between the product design and the manufacturing is that the product design for composites is very focused on the alignment of those individual reinforcement or glass fibers inside of that composite. And we make certain assumptions about that when we're doing the crash analysis or the structural and vibrational analysis of those components. But we have to be certain that in the manufacturing of those parts, are we maintaining that same alignment? So in this case, we're looking at a simulation result where we're analyzing how many degrees of shear or how many degrees of angular change are there for those fibers. And getting this angular shear of more than 10 degrees means that I'm going to have to really consider that, did I do my structural analysis with the right alignment assumed for those individual fibers? Or did I assume that the fibers were all running in a certain orientation relative to the product shape itself? And that's going to distinctly change the results of a structural analysis. So we can't even think about, right? If you're thinking about composite materials, this idea of decoupling the product engineering performance from the manufacturing engineering performance, decoupling those ideas is really just not sensical. You really have to find a way to address those at the same time. Other considerations for manufacturability that people who are in the body manufacturing world might not have realized happen with composites is that you have to really be concerned about this idea of the resin filling. Similar to the challenges that I mentioned in casting, we have to make sure that we have the right formulation of this material in order to assure that we've filled that entire composite body prior to the conclusion of the curing or the polymerization of that resin. Because if that resin solidifies too much, or actually I've been told solidification is the wrong word again, this idea of cures enough, and that cured resin will have a different viscosity. And if the viscosity gets too high, then we see the pressure getting too high. And then we can also see that there would be this distortion of those carbon fibers above and beyond any distortion that happens just due to the preforming of those dry sheets. And that again would change how safely, how confident we were regarding the structural performance of those composites. And these are questions that are not common to people who are working in the auto industry, who are used to, in the body and white manufacturing, production rates of 5, 10, 15, 20 parts per minute. And now we're talking about these composite resin decisions where we might be choosing between, well, is it, 2 minutes per component, or is it 20 minutes per component based on the resin requirements and the resin behavior of the materials we select. And we have to know that very far in advance for this idea of engineering these cars to include composites. And chances are there are currently in industry several examples of people who've come out with composite components for mass-produced cars who are facing these exact challenges today, that the composite manufacturing process that they selected for the material that they selected, it was really a mismatch in piece cost and production time and investment. So if you want to do a good job of planning for and engineering to have the right mix of materials, and you also have to, for the composites, plan for how do you preheat or close or preform those composite dry sheets. Can we infuse those sheets with the resin in the amount of time that we need or allocated for the production rates we want to achieve? Can we cure that resin appropriately so that we get the right reactions? And is that going to introduce a difficult to deal with or difficult to mitigate amount of distortion, or it's not springback, but it's analogous to springback when we think about composites, this idea of the curing-based distortion. And of course, in this idea of this mixed body structure, we still are looking at stamping sheet metal. Stamping sheet metal, probably for the foreseeable future, is still going to be a key component of every body manufacturing program. But that does introduce its own individual challenges. And when we think about the challenges that we have to adapt to for this new future of mobility, we have to recognize that we are seeing an increased use of these newer lightweighting materials, these higher strength materials, such as these advanced high strength steels, these multi-phase, dual phase, hot stamped materials that are used in steel, but also the use of these lower density materials like stamping aluminum, stamping different alloy sheets to see if that will somehow get us the right balance of strength that we need through the material strength, stiffness that is delivered through the material's elastic modulus and its thickness, and also the right weight performance so that we can extend the range of these electric vehicles. We see increasing quality standards regarding shape fixation, and at the same time, we're introducing these materials that tend to have higher amounts of springback. We're seeing many challenges in bringing together and how do we weld these dissimilar materials, these non-typical metallurgies. And when you think about use of steel or sheet aluminum, we hear a lot about Tailor welding, Tailor rolling, patch welding, and other construction options that are increasing the complexity of the conventional automotive sheet steel body or sheet metal body. And of course, the assumptions that come along similar to the other materials that we've mentioned already today. Right, so this means being able to and being well prepared to address this ever-changing material model. Sheet metal, sheet aluminum, sheet steel material modeling is something that's still kind of an evolving science. And we have to, in our engineering and manufacturability organizations, be well prepared to try to address this evolving landscape of these differing materials. We also want to do things that help improve predictive confidence for these manufacturing organizations. And one of these areas where we've seen people in body organizations really run into challenges is this idea of a false positive or a false negative triggered by a decision that I made to run that mathematical model a little bit faster. That in order to make this FEA model run faster, I reduced the number of finite elements, or I reduced the complexity of the mesh, and that made the sample run faster. But it also might give me some false positives or false negatives for the safety of that process. And that one of the things that's doable today is to take away a lot of the necessity to optimize this finite element math in advance and just run with a super fine mesh right from the beginning. And maybe that's my way of improving my predictive confidence in my sheet metal or sheet steel stamping solution. And that by doing so, I can take away any of that question of, oh, early on in my engineering process, I was using a coarse mesh because I wanted my answers to run faster. And then I invested so much time in using this coarse mesh, and that when I go to a fine mesh, all of a sudden the results look different. And we can do away with a lot of that uncertainty if I can just run with a uniform mesh throughout the entire process. And that might be computationally a little bit heavy, but if that reduces the amount of this hand-wringing or uncertainty that I have over did I ask the right model solution questions, I can address that earlier. So one of the things that we've recognized is that we see that there is a good workflow that is achievable if you can, in fact, try to address these issues earlier on. So in this case, we're looking at a stamping and subassembly of two different pieces of sheet metal, the door inner and the door outer, and making sure that we achieve a high level of perceived quality. And this in the past has been very expensive to do, because usually that meant I would run 3 discrete simulations for an inner, for the outer, and for some reinforcement. And then I would try to combine those together and assume that if the individual things work individually, then of course the final thing should work out right. However, we still find that in the execution, certain things can still go awry. And that if I can do so, I can optimize this to get the right assembly ahead of time by avoiding this rework, by simulating the whole assembly process within an environment that allows me to do so. that I can look at the individual sheet metal parts or these individual manufactured parts. I should stop saying sheet metal because we're considering making them out of different materials. And I can simulate the individual parts individually and simulate the subassembly and assembly operation, taking into consideration things like the thermal effects of spot welding, the elastic behavior of the part during closing and the welding operation, and then merge that with the simulation of the joining of the inner to the outer and recognize the accumulated distortion as to whether or not we're inside the window. And this is something that's to do if we're considering all of those parts individually from individual engineers in disparate or dislocated tools. That instead we have to try to find a way to get all of them to contribute into this common assembly. Another thing that's difficult about this idea of predicting the final shape and the distortion of these finished parts is the fact that a lot of the numerical prediction of distortion in the past has been based on an interpretation of these mathematical outputs coming from a simulation code, as opposed to trying to really validate what it looks like in the end. And that's what the very end of the video was trying to show here, is that we've introduced a way of replicating the visual inspection of these components and their accumulated distortion by using a visual visualization method as opposed to looking at these arbitrary numerical parameters to try to describe the overall amount of distortion. And lastly, the challenge that we have, as I already described a little bit there, is that we have to consider, if we are working with this multi-material idea, is how do we assemble these not just sheet metal parts, but maybe that die-cast aluminum reinforcement, as well as that composite door beam. And we have to assemble those individual into a cohesive assembly. The same way that we expect that manufacturers like Tesla and Ford had to do when they incorporated that die casting into their manufacturing environment. So in this case, that means having a timely prediction for the behavior of that inner sheet metal part and that reinforcement that goes where the latch mechanism, or what I labeled the striker, goes. So in this case, we can simulate their formability individually as sheet metal stamped parts, and then consider how are they going to behave when we have to assemble that reinforcement panel to the inner sheet metal and calculate what's it going to be when we take that thick, strong piece of metal that makes up that reinforcement and we weld it to a slightly less thick and less strong piece of material, such as that deep drawn door inner. And that's going to introduce a different amount of distortion than if those would have been very different parts. Similarly, it's a challenge to think about what are we going to do when we have to join this aluminum, die-cast aluminum part, and we now affix its very stiff and very strong structure to that slightly thinner and unreinforced door inner. And what's that going to do to the shape of the door inner that we're trying to complete? And same thing goes for that composite. And I guess the moral of the story that I have to try to wrap up, since I'm almost near the end of my time, is that, well, I've heard this idiom. If the only tool you have is a hammer, then every problem looks like a nail, right? And that's kind of the risk that we have for people who are addressing this future of mobility and the shifting world of manufacturing for the future autonomous and electrified vehicles, is that if we just think of the body as always being this monolith of sheet metal that is welded together, we'll probably just keep making the same old thing that we've always made in the past. But if we want to adapt and be ready for the future, that we need to acknowledge that the individual manufacturing that goes into a body might no longer be monolithically sheet metal anymore, that the joining will not always be welding, that the joining can be screwing and riveting and gluing the car together, and that these different components might come from foundries instead of always from stamping plants, and that some of them will come from composite workshops and not just from stamping plants, and that we have to be ready and adaptable to address this future of manufacturing and recognize that we probably won't end up in a world where there's a magical numerical parameter that comes from my finite element or my computer-aided engineering tools that tells me that the part is the right shape. Instead, I have to look at the springback results, or it's not just springback, the springback and the distortion and the overall final shape of those individual components, and find a way to join them together so that I can predict the visual quality of those parts as opposed to some sort of abstract numerical parameter. And that's going to be a really hard challenge to address if I'm the person whose only tool is a hammer. That I need to be ready to have a broad tool set available to our manufacturing environments to address the fact that that an automotive body in the future is not this monolithic stamped result, that it could be coming from a variety and a range of manufacturing methods. And that brings me to the end of my monologuing. What questions might we have?
Great. Thank you, Eric. Thank you for the great presentation. Now on to Q&A. The first question comes from Jitender. How do we connect robotics layer, MES, and PLM to have an end-to-end view?
So the question was, how do we combine the robotics and the individual FEA, CAE, PLM tools to have an end-to-end view? That's a great question. And the thing is that right now I know, or I suspect, that a lot of times people are aiming for this, and we've been reaching toward the promise of PLM, PDM, that would be this perfect digital twin. But in the meantime, we recognize that it's not. And one of the things that we've been trying to envision for the future is a different way of tracking or connecting all of this instead of just on top of the geometry kernel. And so we've been working on a way to define the product performance life cycle of these new products, that we do have to recognize that there is a predictable and a predictive idea for these different manufacturing tools. So the first part to answer your question is we have to make sure that during the design and engineering phase that people are actually trying to predict what is the as engineered performance expected to be versus the as designed net shape. And we first have to get everybody to answer those questions. And I know that that's an old question to ask, but it turns out that lots of people in the composites industry had not been doing that. And a lot of people in composites manufacturing today, they do their crashworthiness and structural analysis for the composite, but then they, by brute force, just do the manufacturing trial and error to arrive at their manufacturing rules. And that's already creating some break or disjointedness that we need to answer your question. So I think first we have to get everybody to collect the right data. We have to have enough of this predictive modeling for the as engineered state, and we have to have good, reliable models to compare the as built back to the as engineered. And that's one of the things that we've been reaching for with this idea of a hybrid twin, that we're going to use statistical data that we can collect, IIoT on the line, and combine that with predictive modeling that we had generated in the as engineering state, and try to find a way to merge those together. And once we start asking the right questions, we'll be one step closer to the ultimate question you asked, which is, how do we get that end to end? We have to have all the question points for the intermediate milestones. That
Great.
was a very long non-answer. I apologize.
Thanks, Eric. Next question comes from Droll. So you use the phrase carbon fiber reinforced plastic components. He's not familiar with this component. If you can please expand and clarify.
Certainly. So when I was trying to distinguish between a component versus, let's say, a panel or a part, is that when I think of a CFRP, so the carbon fiber reinforced plastic, just think of that as carbon fiber. And it would not be cost effective for me to take a sheet metal stamped door inner, the way we think of it as an individual piece of sheet metal that we start welding and assembling everything together, and replace that one object with a piece of carbon fiber. Because for sure, the piece part production cost would be totally mismatched. It would take maybe $5 to manufacture that door out or door inner out of steel. It would take like $15 or $20 minimum to make that out of carbon fiber. When I say a component, I really try to think of what is the end result subassembly. So in the case of, for example, a seat riser as a component is everything that it takes to make up the distance between the floor pan of my car and the base of my seat, or where my seat like lifting and tilting mechanism would live, right? And in a conventional car, that's maybe 10 different stampings that have been made from individual pieces of sheet metal and welded together. To replace that with a carbon fiber reinforced plastic component, I would try to take all of the functionality of those 10 stampings welded together and try to get all of that functionality in a single monocoque, single combined composite structure that I could manufacture in one step. And so that's why I distinguish that when you make something out of composites, you're aiming for the whole performant body that would have normally have been a subassembly, but now it's just a single component that I ship. And when I said, and then the CFRP, carbon fiber reinforced plastic, that's just a fancy way of saying composites. So composite components. Thank you.
Great, thanks, Eric. Thanks, attendees. That's all the time we have for today. If we didn't answer your question, we'll make sure to follow up through email. Thank you, everyone, and enjoy the rest of your day.